Hello, my name is William,
My name's Luke.
and we will be presenting methods for enumerating polyominoes on finite surfaces. We will begin by defining polyominoes and describing an algorithm for enumerating them on the infinite plane. We will then discuss our methodology for enumerating polyominoes on finite surfaces. Finally, we will compare our results between surfaces and describe some further investigations.
You are probably wondering what a polyomino is. If your first thought is of a domino, you're on the right track, as a domino is a polyomino of size 2. A polyomino is defined as a set of k unit squares that are connected by their edges. Here we have some polyominoes of size 4, which you may recognize as the pieces of Tetris. A common question is to ask, how many polyominoes are there of size k? Before addressing this problem, we must define fixed versus free polyominoes and decide which type we wish to enumerate. Fixed polyominoes are considered equivalent if and only if they can be translated to each other. So here we have 19 fixed polyominoes of size 4. But if we were to look at the free polyominoes, which are the same if they can be rotated or reflected to each other in addition to translation, then this number drops to 5. For the purposes of our presentation, we will be considering fixed polyominoes. To better understand our methods for enumeration on finite surfaces, let's first address the problem on the infinite plane.
The algorithm I will discuss here was developed by Rettelmeier. To ensure that the polyominoes generated are connected, the algorithm recursively grows them from a starting cell. For example, consider starting with the red cell. In each step, we add a new cell to the polyomino that is adjacent to an existing one. After 3 steps, we reach the polyomino as shown. However, one issue with this process is that it generates duplicates. Here, we see that there are 8 ways to generate the same polyomino as before. In order to obtain an accurate count, we must impose conditions on the polyomino's growth to ensure that these duplicates do not occur. First, notice that within the polyominoes at the base of the tree, the starting cell is in different locations within the polyomino. It can be in the lower left, the lower right, the upper left, or the upper right. We can eliminate all but one of these by defining a standard form for polyominoes on the infinite plane. Consider placing our polyomino on a numbered grid. The numbering system will be similar to a matrix, where the row labels increase moving down and the column labels increase to the right. Labels of individual vertices will be specified with the row label followed by the column label, as shown here. To place a polyomino in standard form, we will translate it so that the leftmost cell in the upper row is at 0, 0. For this example, resulting in the following. We can see that a polyomino is in standard form as long as none of the following crossed out vertices are filled, namely those with a negative row number or those in row 0 with a negative column number. Implementing this standard form, we are left with the following tree. We can see that the only remaining duplicates arise due to the order in which the cells are added. To gain an understanding of how to solve this, consider what would happen if we began our process not with a single cell, but with a domino. Beginning with this one, our process would generate all polyominoes containing the red cell and the orange cell to its right. To ensure that the polyominoes generated from the next domino are different from those before, we can disallow any growth to the right of the red cell, since we already counted all of those. Implementing this, we see that there is only one remaining way to generate our polyomino. Ultimately, the logic we use can be extended to all levels of the tree. Once the cell has been added to a polyomino, it cannot be filled in younger siblings or their descendants. Let's summarize the rules we have implemented. First, we develop polyominoes by growing them iteratively from a starting cell at 0, 0, which ensures that they are connected. Second, we define a standard form to remove duplicates from translation, or where the starting cell is in different locations within the polyomino. Lastly, for each cell added to a polyomino, all younger siblings and their descendants cannot include that cell, which removes duplicates due to the order in which cells are added. Applying these principles, we can generate all of the polyominoes as follows. To code this algorithm, we need to determine a data structure which can represent our polyomino. One choice would be to use an array, whose entries are either filled or unfilled. While all k-ominoes would fit into a k by k array, this would require translating the polyomino each time it attempts to grow past an edge. Ultimately, we need to find the minimum size array that can fit all k-ominoes without translating them. And we also need to identify where in this array the starting cell is located. Let's try to find this array for the 4 ominoes. Here, I've included a diagram of a part of the infinite plane. I will show a series of 4 ominoes, and I will use a blue rectangle to keep track of the space they occupy. We can start with a polyomino that extends 4 columns to the right. It could also extend 4 rows down. Finally, it could extend 3 columns left. Ultimately, this shows that a 4 omino can fit into a 4 by 6 array. We can generalize this observation by fitting every k-omino into a k by 2k minus 2 array. With this representation, the starting cell is placed in row 0 in column k minus 2. Below is included a superposition of all 4 ominoes, and as expected, all fit into this array.
So now that we understand Redomaier's approach to the infinite plane problem, we then ask how confining the polyominoes to finite surfaces affects the count. The surfaces we will be considering, namely a cylinder, torus, Mobius strip, and Klein bottle, can all be deconstructed or dissected into a finite grid, where the edges are connected as shown by the arrows. In order to count the polyominoes on these surfaces, we can then consider the polyominoes on a grid and then determine how each polyomino translates in accordance to each surface's conditions. For example, a polyomino on the finite grid is restricted by the edges, whereas the torus will allow the polyomino to translate over the edges onto the opposite side of our 2-dimensional dissection. To start, I decided to enumerate all the possible polyominoes on a finite grid of sizes ranging from 1 by 1 to 3 by 3. This allowed me to get a base for what polyominoes would be possible on other surfaces. As you can see, my hand-drawn examples are sorted by their k values and grid sizes, with the red boxes notating which polyominoes are translations of each other. Each box will only count as a singular polyomino.
We can modify Redomaier's algorithm to work on the finite grid. In fact, we can use the same standard form and rules for adding cells. However, we must find a new size array to represent the polyominoes. As an example, consider the polyominoes on the 4 by 4 grid. We could have a polyomino that fills 4 columns to the right. At the other extreme, we could have a polyomino that fills 4 columns to the left. So, we can use a 4 by 7 array to fit all polyominoes on the 4 by 4 grid. Ultimately, any polyomino on the m by n grid can fit into an m by 2n minus 1 array. The starting cell is then located in row 0 in column n minus 1. When adding new cells using this array, we would have to check whether each one has indices within the array to prevent it from growing past its edges. To avoid the need for all of these comparisons, we can pad our array with disallowed cells, thereby preventing the polyomino from growing past the edges. Additionally, as we grow the polyomino, we must keep track of the number of columns that become filled. Once n columns are filled, we can mark all other columns as unavailable. Implementing the algorithm in Python, we were able to count all polyominoes on the 2 by 2 through 6 by 6 grids.
I repeated the finite grid as a makeshift guide to see what polyominoes would be possible. The torus has the added possibility for cells or individual squares to be connected over opposite edges. This allowed for more possible translations, and if you look closely, you might be able to see that most torus polyominoes on the 3 by 3 grid have 9 possible translations relating to its symmetry, and most polyominoes are translationally equivalent to a polyomino previously enumerated on the finite grid. So even though there are more polyominoes drawn on the previous slide than I drew for the finite grid, we end up with a lower count on the torus than on the finite grid. Why is this? Well, if you look at this animation, you can see how this single polyomino can be represented by different dissections. Here we have all the translations listed out that you just saw animated. And as you can see, these polyominoes on the finite grid cannot translate, as moving over an edge is unacceptable on that surface. However, from the animation, we know these all represent the same single polyomino on the torus. Therefore, these 9 diagrams, which are distinct on the finite grid, will only be counted as one individual polyomino. This results in the lower count for the torus. As I mentioned earlier, many of the polyominoes on the torus were just translations of a polyomino on the finite grid. I'm calling these dissectable polyominoes, since the surfaces can be dissected in such a way that the polyominoes will still be valid two-dimensionally. There were, however, polyominoes on the torus such that none of their translations are valid on the finite grid, which I call undissectable polyominoes. Here, for example, is an undissectable polyomino on the 3x3 torus. It has only 3 possible translations due to its symmetry. Notice how each of these translations has one or more cells that are not connected due to this diagonal of empty cells that translates across the grid. It presents an interesting discovery that there are some polyominoes that can be constructed on a torus, but not on a two-dimensional grid of the same size. This toroidal polyomino with a diagonal of empty cells emerges again and again in higher dimensions. Because of this, I decided to name this particular polyomino an empty diagonal polyomino, or empty anti-diagonal polyomino, depending on the slope of the diagonal. We then found that for any torus of size 3x3 or greater, that the empty diagonal polyominoes are all undissectable, and we conjecture that there are conditions for removing certain cells from the shape to get other undissectable polyominoes.
To modify Weddell-Meyer's algorithm for the torus, the main change we must make is in the definition for standard form. Although in 2D it appears that there is an upper row, in 3D it becomes clear that there is not, and hence the definition used for the infinite plane will not hold. Let's look at a smaller example on the 4x4 torus. For this particular dissection, consider iterating over the vertices on the torus row by row, as shown by this red arrow. If we let filled cells be 1 and empty cells be 0, we can obtain a binary number by concatenating the value of each cell. We let the translation with the maximum binary number be the standard form of the toroidal polyomino. In this case, the cell that yields the highest number is the following. And after translating it to 0, 0, we obtain this dissection. After implementing this algorithm, we were able to count all the polyominoes on the 2x2 through 5x5 tori, as well as up to the 19 ominoes on the 6x6 torus.
To adjust my counts for the cylinder, there were polyominoes on the torus that were not valid here, and multiple translations were no longer possible. Many of the red boxes, which notate translational equivalents, went from containing 9 different translations to only 6 or even 3. This results in more polyominoes than on the torus, but still less than on the finite grid. And by using computer programming, we can see that this trend continues in larger n by n values.
The implementation of the cylinder uses the same standard form as the torus, but there are simply fewer translations that must be checked. And as we can see, the graph looks very similar to that of the torus.
There are other surfaces which we can enumerate polyominoes on that are quite intriguing, but we have yet to create an algorithm for these surfaces. The Mobius strip, for example, offers an interesting twist into our process, pun intended. There are additional conditions that must be met in order for certain translations to be possible. Any translation horizontal to the edge on this surface, which has only a single edge, maintains the polyomino structure. However, for a translation perpendicular to that edge on the 3x3 Mobius strip, the polyomino must have a column of empty cells also perpendicular to that edge. To show why this condition must be met to allow for this kind of translation, take a look at this example of a size 3 center row polyomino on a 3x3 Mobius strip. As shown in the 3-dimensional diagram, this polyomino is completely connected, whereas if we were to translate the row up, then as you can see, the connection is broken, making this a different polyomino in 3-dimensional space. Now, if the conditions were met, as seen here, then a translation perpendicular to this single edge of a Mobius strip would be viable. Although this translation on the two-dimensional diagram does not appear to move the cells in the same direction, it is important to note that we are looking at a two-dimensional diagram for a three-dimensional surface. So by looking at the three-dimensional image, we can tell that this translation would, in fact, maintain the connections of the polyomino. This new condition, however, is more obscure in higher dimensions. For example, when considering the first two size 5 polyominoes on the 5x5 Mobius strip, under the conditions used earlier, the first translation would not be allowed, as there is no empty column. But as you can see, no connection is created or broken by this translation, making these polyominoes translationally equivalent. The second translation in the same direction as before does create a new connection between two cells, and therefore this third polyomino is not translationally equivalent to the previous two. So the defining factor of whether or not a polyomino can be translated a certain way depends on if any connections are altered. This condition can then be extended to the surface of the Klein bottle, where there is the added possibility for connections over the other edge, similar to the difference between a cylinder and a torus. Unlike those surfaces, however, the Klein bottle actually has more distinct polyominoes than the Mobius strip, since the more restrictive conditions for translation means that there's a less likelihood of polyominoes being translationally equivalent. Then, as you can see by my table, even with lower dimensions, we can begin to compare the amount of polyominoes possible for different surfaces of different dimensions. Some things to note about this table: there's only ever one polyomino of size 1 on any surface, and there is only ever one polyomino of maximum size on any finite surface. It also appears that the amount of polyominoes peaks around the middle k value for all surfaces. And there is an apparent trend for which surfaces will have more polyominoes. To better demonstrate this, let's take a look at a comparative graph with higher values.
Here's a graph showing the counts on surfaces that are 5x5. Although the pattern shown in this graph appears in all size surfaces that we checked. Specifically, the torus has the least count, followed by the cylinder, and then the finite grid. Furthermore, the counts on the torus appear to reach a maximum before the cylinder, which in turn reaches its maximum before the finite grid. Some further questions we want to look at include modifying the recursive algorithm to work for the Mobius strip, Klein bottle, and projective plane, enumerating the free polyominoes,
cementing the conditions for undissectable polyominoes of an n by n torus, and formally defining translations of polyominoes on non-orientable surfaces.
Here are the references we used, and we hope you enjoyed the presentation.